Hello everyone, my name is Jalal Hamidash and my domain presentation will be about sampling-based RoboMotion planning. In this presentation, we're going to get to know what RoboMotion planning is, and we're going to focus specifically on the sampling-based method. We're going to get to know the goal of motion planning, the basic motion planning problems. We're going to know what the configuration space is, and then we're going to dive deeper on the classes of motion planning methods. So let's start by knowing what the or giving a definition of what the goal of motion planning is. One of the goals of motion planning is to compute motion plans or motion strategies, and this could be done through different ways. It could be done through geometric paths, time parameterized trajectories, or sequence of sensors based motion commands. The goal of motion planning is also to achieve high level of goals, as we're going to see in this presentation, and that would be going from an initial point to a goal point without colliding with obstacles. And it also coordinating collision-free motions of multiple robots. Like if we have like different robots in an area that are doing different tasks, we don't want them actually to collide with each other or with obstacles. And then assembling a products from a set of parts. So let's start basically by giving an example of a basic motion planning problem to understand what we are actually about to do here. So let's assume that we're going to compute a collision-free path for a rigid object, which is basically a robot among static object obstacles. So basically we have a space, we have robots, and we have some obstacles that are static, not moving, and we're going to try to compute a collision-free path. So our inputs, basically, the data that we're going to provide will be the geometry of the robots, like square, triangle, humanoid robots. Will be the obstacles. The obstacles basically are the impediments on the way of the robots to complete the tasks. And the kinematic of the robots is the robot just, one piece, for example, or it has like hands, legs. Those we call basically degrees of freedom are parts of the robot that move independently. And also we're going to have to provide an initial and a goal configuration. The output that we are going to get actually after computing the collision-free path will be the path or a continuous sequence of collision-free robots configuration from the initial configuration to the goal configuration, basically. It's a path, basically. In other words, it is a path where the geometry of the robot will be fitting from the initial point to the goal point without colliding with any obstacle. So let's go ahead and try to understand what a configuration space is. So clarifying basically the image that we're looking at right now. On the left side, we have the workspace where we can see the obstacles on the dark color, and the robot basically is on the gray light color, which is basically a triangle square shape. On the right hand side, we see the configuration space. So what is the configuration space? The configuration space, C, is the space of all possible configurations of the robot. On the right hand side, you can see that the robot is no longer that geometrical shape. It is basically presented as a dot, basically. And each configuration, Q in C, corresponds to a transformation that can be applied to the robot A. Mapping workspace obstacle to C space to determine set of forbidden configuration for the robot. So in other words, on the left-hand side, we had a geometrical robot with obstacles. So basically, if we move the robot, we're gonna have to be very careful to each angle and each edge of the robot not to interfere with any obstacle, because that would be an impediment on the road. So the simplest way that we do is to find the configuration space, basically shrinking the robot basically to a dot, and making up for the size or the volume of the robot by inflating um, the um, the obstacles. Having those obstacles inflated in such a way will guarantee us a smooth transition of the robot through basically the free area without worrying about the robots colliding with any of the obstacles. I'm going to go ahead and simplify basically this example that I gave with more simplified examples. So in this more simplified example, we have a circular robot of radius c, which is this one right here. We have the Q start, which is the initial point, and the goal point. We have two obstacles, which is Wi and Wj. The question here is there a collision-free path from the start configuration to the goal configuration? Because this is a simple example, we can just basically eye it, look at it, and say, yes, you know, this is a free path. But let's find the configuration space here. So the configuration space is found basically by adding the radius of the robots right here to the obstacles. The obstacles gets inflated on both sides, but you know, the robots basically it shrinks from a circular shape to a dot shape. This will guarantee us a smooth transition of the robots from the start to the goal. So with that being said, the answer is yes. Basically, the robots is safe basically to go from the start point to the goal point, which is the destination. All right, we have another example here. So we have a bigger circular robot with the same obstacles and the Q goal, Q start and Q goal basically. So the question here again, is the robot safe to move? We're gonna go ahead and try to find the C space by adding the radius to the obstacles. As we can see here, we already see that the obstacles are colliding with each other. So basically, there is no way this bigger circular robot would be able to go from the initial point to the goal point without colliding with these obstacles, because its size is way bigger than the space between those two impediments. So this was a simple idea to understand exactly what C space is. So with our C-space being found, we guarantee that our collision detection basically is, or our collision detection system basically is done, and we can guarantee that our robot is not going to collide with any of the obstacles. Next thing to do is to find the motion planning method that we are going to be working with. So we have here many actually classes of motion planning methods. First one is the roadmap method, which represents a connectivity of free space by a network of one-dimension curves. Another one is going to be the cell decomposition methods, which is about to see. It decomposes free space into cells and represents connectivity of free space by adjacency graph of cells. I'm going to give actually examples to clarify each and every one of these methods. The third one that we're going to see is the potential field method. It defines potential function over C space. We're using physics here. So it has a minima of at a goal and follow steepest descent to goal. And the fourth and the last actually method that we're going to see would be the sampling based method, which based on sample configuration in free space and connect them in road map graph. So first we're going to go ahead to and start with the road map method. So what we're looking at here is a visibility graph. So the dark actually a geometrical shape in the middle are basically obstacles, and we can see that we drew actually vertices between nodes that have visible connections. So each node basically is connected to each and every other node when they have visible connection, or when they can basically get connected by a straight line without intersecting with the obstacles. So this is the very first step to find a visibility graph. Once we do this, then we are going to go ahead and reduce that visibility graph. Reducing the visibility graph basically is removing all the non-tangent segments and all the concave vertices to G. So the initial state was like this, and then after actually removing non-tangent segments and the concave vertices of G, we get actually to this graph right here. The connection between those vertices will be basically the path that the robots will follow to get from an initial configuration here, for example, to down here. So the robot basically will go straight this way, down, down, and straight to the goal configuration. Next method actually that we're going to see will be the cell decomposition method. In this method, we follow a different way of finding actually the path from the Q init to Q goal, which is the initial point to the goal point. As we can see actually on the left hand side on this picture, actually we see the dark objects, which are the obstacles, and the initial points, the goal point. So the way we do the trapezoidal decomposition is by drawing actually the vertical line that basically crosses vertices. As we can see, we're decomposing actually this graph to cells. We have 1, 2 is the vertical that passes on this vertex right here. Number 3, it passes on this vertex, but we gotta make sure that we're not crossing the obstacles. We're stopping basically on the obstacle as frontier. So on 4th, we're drawing the vertical on passes on this edge, so on and so forth. We are just giving numbers actually to those cells. And the next step, basically, we're going to find where the Q, where the initial configuration is, the goal configuration is, and obtain a channel from the connectivity graph. Then basically highlights the cells that will take us to the Q goal. And from there, we're going to generate a path in a channel interior. The 4th method that we're going to take a look at is the potential field methods. So this method basically works by simulating the agent as a charged particle, which is going to be attracted to the goal and repelled by the obstacle. So we're using some physics here, and we're using physics formulas basically by creating a repulsion field on the obstacles and an attraction field on the goal. And to control this object, the control inputs basically is the weighted sum of two terms, the attractive term and the repulsive term. This way we ensure basically that the objects or the robot will follow its path actually and get to the goal without colliding actually with obstacles. Next method we're taking a look at is the sampling based methods. We're going to start with rapidly exploring random tree, or as it is called, abbreviated RRT. So So to have actually a robot go from an initial point to a goal point, we generate actually a randomly actually configurations. Once we generate actually configurations, we look like, for example, this is actually a small version, or like, you know, a sub RRT uh, tree, and we're trying to move forward to a goal point. What we do is we generate random configuration. Once we generate random configuration, we find the nearest configuration actually to the edge of our tree. Once we find the nearest, we connect it with an edge, and then once that is done, then we generate again random configuration, and then we look for the nearest. Basically, again, we look for the nearest configuration, and then we connect it to the edge until we get to our destination, which is the goal. It's pretty simple concept. The most important thing basically to focus on is to generate enough symbol configuration basically to to move in small steps and have actually a well organized path. Here we are taking a look actually at an example that I have implemented and I have worked on. This is an RRT holonomic, and what holonomic means in here is that the robots have a free motion. It can move to any direction it wants without any restrictions, like a soccer ball. A soccer ball, it can move forward, backward, right, left, diagonally, or any direction. So basically, this green dot right here is the initial point. The red one actually is the goal point. This geometrical shape that we see here are obstacles, and as we can see, the tree is well spread in the area. That's what I meant actually by generating enough configuration, is have the tree to be well spread actually in the area to give you a well organized path. So the path, as you can see, is avoiding obstacles here, and every single time, every little, actually you can see actually that we have those edges. Those are tiny edges that connects one node or one configuration to another. This graph, however, is for the same basically sampling based method, which is RRT, but this case is for non-holonomic motion. What we mean by non-holonomic motion here is the robots cannot freely move in any direction it wants. It is more like an object or robot that has moving restrictions, like for example a car-like robot. A car can go forward, backward, but if it wants to move to the right or to the left, there is, for example, a 3-point turn that it needs to do, or it needs basically to move in a certain fashion. So the robots here have motion restriction, and as we can see, the graph looks completely different in here, as the robot is close to the obstacle. It cannot just move to the left, but it needs to do a certain motion basically to avoid the obstacle. Next simple and based method that we're going to see is an RRT star. RRT star is like RRT, but it doesn't just give a path from the initial to the destination goal, to the destination point. It gives you the shortest path between the initial configuration and the goal configuration. Um, so our goal here is the best case scenario, or the best path, or the shortest path between 2 points. So the initial or the basic step for RRT star is somehow like RRT, but there is a huge difference actually afterward. So from a node, basically, we generate enough random nodes, and we look basically for the nearest one to that node. So once we find it, we call it like Q new. We don't connect it to the parent node. We just mark it. We remember that node that we're going to work with it. So once we mark it, basically we look in a circumference of like a certain radius of the nearest node to the one that we found. Although we started from this node and we look from this node and we looked for the nearest one to this node, we look again actually if there is another node that is near to this one. If we find it, when we find actually the nearest one, we connect it as a parent and as a parent to the node found. And once that is done, we do what's called a rewiring process. The rewiring process basically means we find basically the shortest path to this node from the initial point. So although this node, for example, might be the nearest one to this guy, but it might cost us more to go to this node, which is our destination, through this path than going actually through a different one. So once we find the most optimized or the shortest path to this node, then we redo actually the whole process again until we get to our destination. Again, I'm providing actually an example of the RRT holonomic RRT star. This is a holonomic motion where the robot is free to move at any direction, and we see this is basically the most optimized or the shortest path from the initial point to the goal one, and this one, which look pretty different, is the RRT non-holonomic motion. So the non-holonomic motion again is the motion where the robot has constraints in its motion, and as we can see, we successfully actually moved from the initial point to the goal point through this path. These were actually different kind of RoboMotion planning methods, and with that, I will open it to questions. Please feel free to ask any questions if you have one. Thank you for your attention.